Chapter 9 is going to start with getting into what really chemistry is all about. So we're going to talk about stoichiometry in this chapter. We're going to start with section 9.1 and 9.2, which is going to cover the information given by chemical equations. It's just a quick review of the information that's given from a balanced reaction. Then we're going to do some calculations with mole-to-mole relationships. This is just a review, like I said before. So remember that a balanced chemical equation gives us the relative number of atoms or molecules or moles of reactant and product in a chemical reaction. The coefficients of a balanced equation gives us the relative number of molecules. So here we have a balanced equation. The equation's balanced. We know that we have 2 carbon on this side, 2 carbon on this side. We have 5, 6 hydrogen on the left. We have 2 times 3, which is 6 hydrogen on the right. We have 2 times 3, which is 6 oxygen plus this one, so there's 7 oxygen. 2 times 2 is 4. 1 times 3 is 3, so 4 plus 3 is 7. 7 oxygen on the right, so it's balanced. That means that we have conserved the molecules within the reaction. So we started with X number and we ended with X number, which is really important when it comes to the laws of conservation of matter. So all atoms present in the reactants are accounted for. So I could say 1 molecule of ethanol reacts with 3 molecules of oxygen to produce 2 molecules of carbon dioxide and 3 molecules of water. I could also say 1 mole of ethanol reacts with 3 moles of oxygen to produce 2 moles of carbon dioxide and 3 moles of water. We've kind of talked about that in Chapter 8, how we can look at these as individual molecules, or we can look at them as a mole, which is the 6.022 times 10 to the 23rd of anything in a mole. All right, so let's look at the concept check. One of the key steps in producing pure copper from copper ores is this reaction, and it's unbalanced. After balancing the reaction, determine how many dozen copper atoms would be produced from a dozen molecules of the sulfide and 2 dozen of the oxide. Also, how many moles of copper could be produced from 1 mole of the sulfide and 2 moles of the oxide. We can balance the reaction by putting a 2 in front of the copper 2 oxide and a 6 in front of the copper. So now that it's balanced, let's write the information that we know underneath. After balancing the reaction, determine how many dozen copper atoms. So I'm going to put X dozen underneath the copper because that's where we want to go. Could be produced from a dozen molecules of the sulfide. So we write 1 dozen here, and 2 dozen of the copper 1 oxide. And then also, how many moles? Let me change colors to write the second part question down. We'll write it above it. Also, how many moles of copper would be produced from 1 mole of the sulfide and 2 moles of the oxide. Let's start with the question with the dozens. So if we were going to make this on a smaller scale, we would look at, let's say, a dozen of these molecules, and we have a dozen of these, 2 dozen of these. Well, in the balanced reaction, the coefficients are 1 to 2. So this says if I have 1 counted number of this plus 2 counted numbers of this, I should produce 6 individual coppers in that case with if we're looking at molecules or atoms. So if I have 1 dozen copper 2 sulfide atoms or molecules and 2 dozen copper 2 oxide, how many dozen should I make here? Well, if it's 1 to 2 here makes 6, then 1 to 2 here should also make 6. So that should be 6 dozen. Come back up here and let's look at moles, because that's what we want to deal with. Moles are easier for us to handle. I can go into the lab and tell you I need you to find the mass of 2 moles, and you actually could mass that out and see how much that is. So we have 1 mole of copper 2 sulfide, 2 moles of copper 2 oxide. How many moles of copper metal does that produce? And the answer then again is 6. So we end up with 6 dozen molecules or atoms of copper, or 6 moles of copper, depending on what we start with. All right, now let's look at the mole-to-mole relationship. We're going to do some calculations with some of these. So a balanced equation can predict the moles of the product that a given number of moles of reactants will yield, just similar to the question we just looked at. And we can read this reaction as 2 moles of water decomposes to form 2 moles of hydrogen and 1 mole of oxygen. If I double this recipe, if I start off with 4 moles of water, I would get twice as much product. Just like if you would start off with 2 cake mixes, you end up with 2 cakes produced instead of 1. So I have 2 moles of water. If I had 4, I would produce 4 moles of hydrogen and 2 moles of oxygen. So it's just a multiplier of 2. The mole ratio allows us to convert from moles of one substance in a balanced equation to moles of a second substance in the equation. Let's look at this example. This is how I want you to set every problem up that you're going to do. We're going to use the balanced reaction, and we're going to put information underneath the different compounds in the reaction. So it says how many moles of NaF, so I'm going to come over here and I'm going to put X moles, or Xm, will be produced if 3.5 moles of sodium is reacted with, let's put moles over here, with excess Na2SiF6. And I put excess just because this is how I shorthand things. So this is the same thing as saying excess. And that just means that it doesn't matter how many moles of sodium I have here, I have way more of this than I'm going to need. So this will come into play later in the chapter when we talk about limiting reactants. But for right now, we're just saying we have more of it than we need. So it wants to know how many moles of NaF will I produce if this happens. Well, what we're going to do is use the information given in the balanced reaction. We're going to start with the 2 things we're talking about. So we're talking about sodium, so I'm going to put Na, and then I'm going to put NaF here. And I'm going to do a ratio. The top one is going to come from the balanced reaction, so bal reaction. The bottom number is going to come from the problem. So I go to the balanced reaction. The balanced reaction tells me that 4 sodium, and I get that right here from the coefficient, is going to produce 6 sodium fluorides. That's not what the problem has, so let's put our line underneath them. The problem says I start with 3.5 moles of sodium, and I want to know how many moles of sodium fluoride that I will get as a product. So we're going to do this with the ratio. You're going to cross multiply. So we say 4 times X equals 3.5 times 6. Then we're going to divide both sides by 4, and this is where it comes in really handy to know your basic algebra skills. That's why you're in Algebra 2 in order to be in this advanced class, so that this isn't a problem for you to do mathematically. We throw that in the calculator and we get the answer 4. And you can't just use the number 4. You have to tell me for what. This is a mole to mole ratio, so this is moles, and it's of NaF. So you have to put not only the unit, but then you also have to put the name or the compound after it, the symbols for the compound. So what we did was we started with moles and we found moles. So back in the little scheme of things from the last chapter, when we had grams and moles and Avogadro's number, remember this? We had grams and we have moles and we have molecules. And we talked about how in order to go to moles, or to get to moles, and you're at grams, you have to go grams to moles. We said that came from the periodic table. And then we talked about if you're at moles and want to go to molecules, this is where you're going to use Avogadro's number. And if you're at grams and you want to go to molecules, you have to go through moles in order to get there. Or molecules back to grams, you go through moles. Well, in this case, we were given moles and we wanted to get to moles. So this is a mole to mole ratio that we're going to use. And it's really important, especially during the beginning part of the chapter, that you set it up like this, that you make sure that you write down your little note-taking things here, like the names of the compounds or the formulas of the compounds, and that you write down the balanced reaction over the problem. This helps you to find your mistakes, helps me to find your mistakes so I can help you as you do the more advanced problems. This is just the beginning of the problems we'll work on this chapter. We're going to finish up the lecture in 9.1 and 9.2 with this final problem. One of the things that I want you to do is if you think you have a handle on this or you at least want to try it, this would be a good place for you to go ahead and pause the video and see if you can't work the problem out yourself. If not, go ahead and watch the steps. Take time to write out the steps on your notes so that I can tell that you've watched the video, and we'll go from there in class so I can help you a little bit closer individually. So propane, C3H8, is a common fuel used in heating homes in rural areas. Predict how many moles of carbon dioxide. So you have to find your written clues as to where your X's need to go and what units we're looking for. So predict how many moles of carbon dioxide. So you're going to come down here and you write X moles under the CO2 are formed when 3.74 moles of propane are burned in excess oxygen. And there's excess again. We just shorten it like this just to let you know that we have way more than we need. And this, like I said, is going to come into play when we do limiting reactants further along in the chapter. So we're going to look at it and set it just like the problem that we just did. We write down the information we have. We're going from moles to moles. So I write C3H8 and CO2. Remember that my top number is going to come from the balanced reaction. Now, if you are familiar with ratios, you know that it doesn't really matter if I put the balanced reaction information on top or from the problem on top. It's just that we have to be consistent so we don't mix them up. So I always go with the balanced reaction. So we have 3.74. Oh, that's from the problem. Let's go back and get the balanced reaction. Sorry. Okay. 1, because that's your coefficient here, and carbon dioxide is 3. And on the bottom, we're going to put, from the problem, we have 3.74 moles of propane, and I want to know how many moles of carbon dioxide that is. I'm going to cross multiply, so I have 1x equals 3 times 3.74. I'm going to put that in a calculator, 3.74 times 3. And we come up with 11.22. That's moles. This is a mole to mole ratio. That's moles of CO2. You're going to make sure that you put a box around your answer. Make sure that you have a unit and that you have the substance that that unit pertains to. And another good thing to do is to go back and look at it and say, does it make sense? If 1 mole produced 3 moles of carbon dioxide, 1 mole of propane produced 3 moles of carbon dioxide, and I'm more than tripling that, I should also more than triple my amount of product. So if this were multiplied by 3 or 4 even, it's closer to 4, then this number should also be multiplied by 3 or 4. So anywhere between 9 and 12, and if you look down here, we notice that it's 11.22 moles of carbon dioxide. So not only did we set the problem up correctly, show our work correctly, box in our answer the way it should be, we go back and reason and see if it makes sense, and in this case it does, so that's probably the answer that it's going to be. So like I said before, make sure that you have all of this information written down just like I put it on the flip video, and we'll be able to work with that in class.